So today, the thing I want to talk about, you see that here's the title, and here's the title. You see that there are several components in this title. So the first thing we are going to talk about is we are trying to talk about sampling problem. So actually in the talk, including the talk by Ting Wei and also the talk by Professor Lin yesterday, they've already briefly mentioned some kind of sampling problem. So I will also try to talk about some kind of algorithms that we are using to tackle non-smooth sampling problem. And then the second component I'm trying to using is something so-called the regularized Wasserstein Proximal operator. So this is actually something already been mentioned by Siting's talk and Marco's talk today. And the reason that we want to apply this kind of regular Wasserstein Proximal operator is somehow we realize that this kind of operator is some kind of approximation to the JQ scheme. And with this kind of approximation, we can somehow construct some kind of implicit scheme, so in order to discretize the probability for ODE. Then the last thing that we want to use in this work is some kind of splitting technique. So the reason that we want to use the splitting technique is, for example, if we do not have this kind of splitting sense, the thing that I'm going to talk about in the next maybe 40 minutes can only work in some kind of low-dimensional case. But as you may know that for this kind of data science area, whenever we have some kind of algorithm, we definitely have to push this kind of algorithm to the high-dimensional case. Because otherwise, if I always talk about some kind of algorithm that only works for one or two-dimensional case, you will think about I'm just playing with those kind of equations. It will never gonna be something useful in practice. So in order to make our algorithm to be something that is practical in some kind of real application, so we have to use it some kind of splitting technique. So essentially, this is some kind of joint work with my postdoc advisor, Professor Stanley Osher, and also Professor Wuchen Li from the University South Carolina. So the idea or the thing that we are trying to do here is we are trying to draw some kind of samples from some kind of distribution. And for this kind of distribution, we assume that we somehow has the access to the log density. For example, we know how to compute or we know how to evaluate the capital Vx over here. However, somehow we do not know exactly this kind of normalization constant. So in that case, it creates some kind of difficulty in order to draw some kind of samples. Okay, so for our work, the thing we are particularly interested in is the case that we have some kind of composite structure in our log density. So we assume that we are trying to think about the scenario that the log density V can be written as a summation of two terms. And usually you will see that usually we will assume that for the first term F, it's going to be some pretty nice term. It's going to be some kind of smooth term. However, for the J term, usually it will be some kind of non-smooth term. Just as what Ting Wei mentioned in the end of her talk, usually for many cases, we care about something like the L1 regularization. And also for the imaging community, like what Stan did for many, many years, like the total variation regularization, for many, many cases, this kind of J could be something that is non-smooth. It could be either you can think about the L1 norm or the TV regularization norm, which will be something that is pretty non-smooth and create difficulties in getting this kind of sampling sense work. So this is the things we are trying to think about. And for the application of our algorithm, of course, I will give you some kind of numerical experiments in the end of this talk. But somehow you can think about that for the application of this kind of general setting. For example, for the first application, we can think about the Bayesian inference. And you can think in that case, this F function, it could be simply the likelihood function. At J, it will be some kind of priori distribution. So in that case, we are just trying to draw some kind of samples from the posterior distribution and this kind of J, which could be something that is non-smooth. And the other application is definitely something that happens in the generative modeling. So assume that this kind of function V is some kind of parameterized neural network that approximates some kind of data distribution. And the reason that we want some kind of J term over here is we hope that the samples we draw from this kind of neural network will have certain regularization effect or will have certain property. For example, some kind of sparse property, or for example, which will be some kind of smooth image, like we impose a total variation regularization. So this is some kind of general setting that we are trying to think about. And then again, there will be some kind of more background, and I guess for many of sense that showing here also appeared in the Professor Lin's talk yesterday. So the idea or some kind of quantity we are using is some kind of Kerr divergence. And one of the perspective we'll keep thinking about our work is we will regard this kind of sampling problem as some kind of infinite dimensional optimization problem in the probability space. So the reason that we want to view this kind of sampling problem is in the probability space is it's not only help us to develop some kind of algorithm, because somehow you will know that for the optimization community, this kind of splitting idea is something that is non-standing, is something super popular, and we are trying to use this kind of splitting technique also in this kind of sampling task. And the other reason that we want to use this kind of optimization technique, or the reason we want to view the sampling problem as an optimization problem is later you will see that, of course, for example, for the work by the Webseno in 2018 and also the work by the French group in the 2019, the way that we show the convergence of our algorithm will also be using some kind of tools from the classical optimization theory. And later you will see that the way that we show the convergence of algorithm is essentially using some kind of convex optimization tools to show some kind of decay of the energy term. So that's some kind of way of thinking about the sampling problem as some kind of optimization problem in the probability density space. So for here, once we think about the sampling problem as an optimization problem, then one natural thing is thinking about the one-time gradient flow of this kind of Kerr divergence is something classical. We know that the one-time gradient flow of the Kerr divergence will give us this kind of one stochastic differential equation. We will have some kind of drifting term, which is a grad way, and also we have some kind of Brownian motion term over here, which give us the diffusion. So this is something that's so very classical one dynamic, and we know that there are lots of excellent works that based on certain discretization of this kind of dynamic, for example, the unadjusted one, and also if we have some kind of adjustment term to the standard Wunga, which is this kind of metropolis adjustment one algorithm. So actually, it's similar as what I have mentioned in the Professor Lin's talk yesterday. This kind of algorithm is still some kind of dominating algorithm in practice. So basically, they are based on some kind of forward Juncker discretization to this SDE. And we will have some kind of reasonable algorithm in order to get reasonable samples that approximate the target distribution. Okay? So however, some kind of issue about this kind of discretization based on this kind of one dynamic is the first issue over here is you see that for whatever the Wunga or whatever this kind of Manga, the issue here is we have some kind of Brownian motion term. So the Brownian again, I have to recall the excellent talk by Professor Lin yesterday. So if you recall that there is a cartoon in the Professor Lin's talk that he's showing that for this kind of unadjusted one, it somehow usually takes you forever to hit the correct global minimum because somehow this kind of Brownian motion term will not give you the sufficient exploration. So that's some kind of issue for the Brownian motion. And the other way to think about the issue of this kind of Brownian motion term is from the classical stochastic analysis with some probability theory. We know that the variance of the Brownian motion is going to be the dimension d. So that means this kind of algorithm will become very, very bad when you go to the high dimension. So this is another reason that this kind of unadjusted one type algorithm will not be something that works so well in the high dimensional case compared with the low dimensional scenarios. This kind of Brownian motion term really give us some kind of trouble. So given this kind of observation about the classical algorithm, the thing we are going to do, or the goal for our work is we are trying to think about these three goals. So these are the three goals that will guide us to design our algorithm. So the first goal is we are trying to use some kind of deterministic implementation. And the reason that we want to use some kind of deterministic implementation is we are trying to avoid the Brownian motion. And the way that we can avoid Brownian motion is by using the excellent score function, which is keep being talked about in the past 4 days. I guess for like more than half of the talk, they always mention this kind of score function. It's something that's so good, it's something so excellent, everybody uses it. And also the same for us, we will use a score function. And then the second goal for our algorithm is we are hoping to have some kind of time-implicit discretization, something very similar to the JKO scheme, but later I will mention that for the JQ scheme, it's not going to be something that easy to compute. So we want to have some kind of approximation to the JQ scheme that is much easier to evaluate. However, we still try to keep some kind of time-implicit nature of the discretization. And the reason that we want to have some kind of time-implicit discretization is usually this kind of discretization will allow us to work with a larger step size and also allow us the algorithm to be something that is more stable. Okay, so this is the second goal. And finally, for the third goal is we hope our algorithm to be something that is scalable into high-dimensional case. We want our algorithm to be something that can be really used in practice, not something that is only some kind of play around with the equations. We want something that can be applied with real-life problems, so that we want to some kind of splitting techniques. So the next thing is we are trying to talk about the way that we try to avoid the Brownian motion. And in that case, we simply consider this kind of so-called probability for ODE. In that case, we generate essentially the diffusion by the score function term over here. Okay, and for the first term, the drifting term is actually the same. It's actually the same with the classical adjoint dynamic. And the only difference here is we generate diffusion by the score function term. However, one thing that you will immediately observe is for this score function term, it's going to be something that is very difficult to approximate. I know that for most of people over here, you have some kind of experiments. For example, you do the score matching, you do some kind of neural network approximation to this kind of score function. It's going to be something that is very difficult to approximate. So that's the reason that in the next slide, I will show you the regularized Wasserstein proximal operator. Okay, so before we talk about the regularized Wasserstein proximal operator, we think about what happened to this density function. So we know that for this kind of score probability for ODE, the continuity equation of this ODE is simply going to be the Fuqun equation. So that means the evolution of the density is going to be governed by this Fuqun equation over here. So in that case, you can just imagine that in order to get an approximation to the Fuqun equation, or in order to get an approximation to the score function term, the thing we are going to need to do is we are going just to find some kind of ways to approximate the evolution of the Fuqun equation. And the most classical way to approximate the evolution of the Fuqun equation is definitely the JQ scheme, which is already being mentioned in the Professor Li Wang's talk on Tuesday, something very similar. So one of the very popular way to do this is using the JQ scheme. For the JQ scheme for here, we have the KR divergence. So essentially, this guy is some kind of analog of the proximal point in the classical optimization theory. So in that case, we have some KR divergence over here, and we have some kind of Wasserstein 2 distance in the second term. Okay, so this is the classical JQ scheme. And the way that we can rewrite this kind of JQ scheme a little bit is we recall this kind of Benamo-Brenier formula, which is also appears in the Sitting's talk. So we can write down the dynamic formulation for this kind of Wasserstein 2 distance. So in that case, we will have the KR divergence plus this kind of transportation energy. And for in that case, we also have some kind of constraint, which is the continuity equation over here. And also for the initial condition for this rho, it's just going to be the rho k in the previous time. And for the rho h, it's going to be our the approximated solution for the Fuqun equation at the next time point. Okay, so this is essentially the dynamic formulation for the classical JQ scheme. And then you may know that for this kind of JQ scheme, it's actually something very difficult to solve because it's a high-dimensional optimization problem. And I guess in the Xuefeng's talk this afternoon, or in her poster, she will also talk about some kind of way to approximate this kind of JQ scheme in the by the neural network. It's going to be something very difficult to do. However, something we can do to approximate this kind of JQ scheme is we think about something so-called the regularized Wasserstein proximal operator. Something has been mentioned for many times, for at least twice in this workshop. So the definition for this guy is defined as we are having some kind of cross entropy term over here, and also we have the similar transportation energy over there. And then for the constraint for this optimization problem, we are going to have some kind of viscosity term, or we are going to have some kind of absorption term over here. Okay, so definitely when when you first look at this kind of RWP operator, you will feel a little bit confused about why we define things in this manner. But this is actually a very nice connection between this operator and the classical JQ scheme. Is if we do some kind of very simple substitution, something like this, we can say that this kind of regular one-side proximal operator is actually equivalent to some kind of feature information regularized JQ scheme. So, for example, if we do some kind of substitution like this, you will see that the equation, the constraint over here, will simply become the continuity equation, and somehow you just do some kind of change of variable and the integration by part for like 2 or 3 times, you will arrive that the optimization functional will be the same as this guy. And if you compare this formulation and the classical JQ scheme over here, you will see that we only have some kind of extra term, which is some kind of feature information regularization term over here. So this is exactly the same regular one-side proximal operator as in here. So basically, these 2 formulations, they are equivalent with each other. And indeed, this kind of feature information regularized JQ scheme had appeared in the literature like 5 years ago, also by some kind of excellent work by Professor Li Wang. And they also talk about some kind of regularization effect provided by this kind of feature information term. And somehow you can see in that case, we have some kind of way, we have some kind of new formulation, or we have some kind of regularized version for the JQ scheme. However, however, once we reach this point, it's still somehow not so clear that the reason we want to talk about this form. So the most important reason that we want to talk about this kind of RWP operator or whatever this kind of feature information regularized JQ scheme is for this optimization problem, we have the excellent closed form solution to this optimization problem. And actually, this is something also appeared in the Tingwei's talk. Once we look at this kind of RWP operator and we introduce some kind of Lagrange multiply capital phi, and we use the first order of probability condition, we can transform this kind of constraint optimization problem to a system of coupled PDE. We are going to have a forward Fuqun equation and a backward Hamilton-Jacobian equation. So in that case, for this system equation, using the very nice log transform also mentioned by Tingwei, we can, which is also simply the hopeful co-transformation, we can somehow linearize this kind of system of coupled PDE and transform this Fuqun and Hamilton-Jacobian equation to a system of heating equation, which is something happened in the next slide. And I guess in the Tingwei slide, you also see something very similar like this. We will transform the coupled system PDE to this system of forward backward heating equation. And the most amazing thing for the heating equation is we know exactly how to approximate or how to evaluate the solution of the heating equation by using the heat kernel. And that's the reason that in the next formula, you see some kind of heat kernel over here. So essentially, this kind of heat kernel comes from the solution of the heating equation over here. Okay? So once we arrive at this kind of system of backward forward heating equation, somehow we're just using the technique of heat kernel to write down the solution to this kind of regularized one-side proximal operator over here, which is given by this kind of kernel formula over here. So actually, this very nice kernel formula is discovered by Siting in 2023, and so essentially you can imagine that this formula gives us a closed form solution to the RWP operator. It gives us a closed form solution to the feature information regularized JQ scheme. So this is the most important reason that we want to talk about this operator. This is the most important reason that we can somehow employ this operator to get some kind of implicit scheme, but with closed form update. So that's the kernel formula over here. However, once I introduce you this kind of kernel formula, you will still have some question, I guess, because for here, we have some kind of crazy integration in the D-dimensional space. And although for this integration, it's going to be something that is easier to solve compared with the original sampling problem, because somehow we have some kind of regression term over here. But it's still for the genetic capital V or for the genetic log density, it's going to be something still difficult to solve. So essentially, actually, I learned this from the Professor Hao Ming Zhou's talk on on Monday or Tuesday. On Tuesday, he talked about when we have some kind of problem in the high-dimensional case, we have two ways. So either you sacrifice some kind of accuracy or your function is simple. So actually for our work, we exactly take the same two directions. So for the first direction, we assume that our function is simple, which means we can use some kind of tensor to approximate this kind of density term. So you can imagine that if the function has a certain low-dimensional structure, we can use some kind of tensor to approximate the term over here. And for the hit kernel, is something that is super nice. Definitely, we can use some kind of tensor trick to approximate this kind of hit kernel. So in that case, we will have some kind of iterative formula that is totally written in the tensor format. And once we write something that in the tensor format, it will be very, very easy for us to approximate this kind of integral, because we write everything in some kind of low-dimensional tensor. And somehow it's equivalent to that which already discovered the low-dimensional structure of the function. So this is corresponding to the first case of the high-dimensional integration. And the second case we will talk about is the major case I will talk about today is we try to do some kind of sacrification on the accuracy. We try to use some kind of approximation to that kind of formula. We lose some kind of accuracy, but we somehow try to keep the validity of the algorithm, or we are trying to keep some kind of convergence algorithm, but we lose some kind of accuracy because we use some kind of additional approximation to the integration over here. So the additional approximation we are using, there actually will be two approximations. The first approximation is going to be something so-called the Laplace approximation. It's something very classical, I guess, in the statistical community. So the idea of the Laplace approximation is for such an integration, for some kind of exponential function, the value of this integration will be dominated by the maximum value of the exponent over here, which means it will be dominated by the minimal value of the function inside over here, which is the capital V plus the square term over 2h. And once we look at this term over here, capital V plus z minus y square over 2h, what reminds you? This reminds us the classical proximal operator. We exactly have some kind of structure like the classical proximal operator appears a lot in the optimization book, in whatever optimization book. So in that case, you can imagine that the integration over here, it can be somehow approximated by this one single point, and this one single point is somehow evaluated at the proximal point of the function capital V. So because for here, this is nothing but the proximal operator for the function capital V. Okay, so you see that, and however, one thing that I want to remark over here, the constant C is actually some kind of very bad constant, and later I will give you more details about what the constant C looks like. But the thing I will promise to you is by using this kind of Laplace approximation, we can get some kind of reasonable approximation to the integration over here by using some kind of proximal point of the original function. So this is the first approximation we are doing. I'm using the Laplace approximation. And then the second approximation I'm going to do is I'm going to use the splitting. So you see that for the previous approximation I'm having over here, somehow I'm trying to assume that I know exactly this kind of proximal operator. But definitely you may know that for the proximal operator, for whatever function, for general function, it's going to be something, again, difficult to solve. So in that case, we're just using some kind of so-called splitting technique. We are trying to split the log density. You recall that for our log density, I assume that it's going to be something like f plus j. I just try to split this kind of log density into two parts. The first part is f, and the second part is j. And somehow we just try to think about, okay, in that case, usually we know the exact form for the j part. For example, for the case of L1 norm or the L2 norm, or for many useful regularization terms. In that case, we actually know the proximal operator of those kind of norm. So the idea of the splitting is we try to revisit this kind of KR divergence, and we can decompose the KR divergence into three terms: the energy term with respect to F, the energy term with respect to J, and some kind of entropy term in the end. So the way we will do is we will do some kind of splitting scheme, and the splitting scheme goes like follows. We first try to minimize or talking about the gradient descent with respect to the first part, so that we have some kind of push forward operator over here. So this is the first step. We are trying to think about the gradient descent with respect to the first energy term. And for the second step, we are trying to do some kind of implicit step, which means we are trying to compute the minimum of the energy term associated with J, and also the entropy term, and also with some kind of Wasserstein distance over here. And something that you can see that very interesting over here is for the first two terms, we can do some kind of combination. And if we call this rho J star as the density with as a per bit density with the log density of J. So in that case, we can rewrite the second step as a KR divergence plus the Wasserstein distance. So what reminds us, this is exactly the JKO scale. Okay? So, and however, the most amazing thing over here is for the second step, our target density is only something with respect to J. And we somehow, for the J term, we just recall that it's a regularization term. And for the regularization term, for example, the L1 norm, we know exactly the proximal operator. And once we know exactly the proximal operator, we can somehow get a reasonable approximation to the whatever regularized Wasserstein proximal operator that I showed to you in the few slides ago. So this is the splitting we are using. And once we got this kind of iteration in the density level, the next thing we can do is we can think about what happens in the particle level, because we are trying to do some kind of, we are trying to propose some kind of particle algorithm to draw samples from the target distribution. And of course, for here, you see that I use the word propose, because actually the formulation over here, the particle formulation over here, compared with the density level formulation, there's actually still some kind of distance. And for the more details, we can talk about offline, or we can you can look at our papers. But somehow we can use this kind of particle iterating scheme to approximate the previous density level iteration. So in that case, you see that the first step is simply the gradient descent with respect to the smooth energy term F. And for the second term, it's going to be some kind of so-called semi-implicit step. So for the first step, for the first part, we are using the proximal operator, which is implicit gradient descent corresponding to the function J. So this is the first part. And for the second part, we are using the regularized Wasserstein proximal operator. And you just recall that because for this operator, it approximates the JKO scheme. So in that case, it means this guy K, the kernel K, applies on the density as rho K plus 1/2, we will get some kind of approximation of the density at the time Tk plus 1. So you see that the reason that I call this scheme as some kind of semi-implicit scheme is somehow we are trying to use the information, or we are trying to use the score function at the time Tk plus 1. So that's the reason that I call this scheme as a semi-implicit scheme. However, if you look at very, very carefully on the right-hand side of the second step, you see that everything on the right-hand side, they are somehow explicit. They only depend on the information at the time Tk plus 1/2. So in that case, you see that this is essentially some kind of closed form update. We do not really need any optimization. We do not really need any very difficult approximation or optimization that appears in the JQ scheme. We just have some kind of closed form update for the right-hand side. Okay? So that's a particle approximation. And one thing that I want to say in more detail is for the case that J, the regularization term, is going to be the L1 norm. So actually, for that case, we have very, very nice formula. And so just some kind of recap is for the proximal operator or the L1 norm, it's going to be the soft thresholding. It's going to be some kind of something that actually very close to the remove function. And so this is the proximal operator or the L1 norm. And once we record this kind of explicit form for the proximal operator or the L1 norm, we can just plug in everything we talked about before, the Laplace approximation to the kernel formula, and somehow we can get some kind of approximation to the gradient log of the rho K plus 1. So this guy is an approximation to the rho K plus 1. We can get the score function at the time Tk plus 1, some kind of approximation. And for here, you see that for this kind of U, is simply, you can imagine that this guy is simply some kind of interacting kernel that controls how the particles should interact with each other. Oh, I can use this. So in the next slide, I give you the final algorithm we are using. And one thing that is very, very interesting here is, actually it appears in the Professor Renyi last talk. He pointed out some kind of connection between the non-local model and the modern transformer structure. And somehow you can see that even we try to develop some kind of sense from the purely this kind of OD or some kind of stochastic analysis perspective, we actually arrive something that's very, very similar to what happened in the modern machine learning architecture. So you see that for here, our iteration, especially for the second step iteration, we have some kind of interaction over here. So essentially, this is the term that gives us some kind of interaction of particles. And for the interaction of particles, based on our kernel formula, this kind of interaction of particles is given by some kind of formula like this. And this kind of capital A is some kind of exponential of this kind of interacting kernel. And this guy, M, is nothing but some kind of softmax function, which I guess also appears in the several talks in this workshop. So we have some kind of very similar structure like what happened in the modern transformer structure. And I guess this kind of observation gives us some kind of new idea about how we can use this kind of classical thing to develop or to derive some kind of more mathematical inspired machine learning architecture. So this is some kind of observation that we are having and also something that we are doing currently. But this is not really the central topic for this talk. So again, anyway, so this is our iterative scheme. It's essentially some kind of deterministic interacting particle system that will help us to draw samples from some kind of target distribution. So of course, for here, we have some kind of convergence guarantee. And I will not really go into all the details for this kind of convergence guarantee. But the thing I will say is, for the case that we have some kind of smooth distribution, and the reason that I put the smooth distribution as the first theoretical result is, for this case, we can get some pretty nice result, especially for the case of the, we can get some kind of exponential convergence. And for the case that we consider the Renyi divergence between the target density and density we generated, we can have some kind of exponential convergence over here. Okay, and the reason that we consider the Renyi divergence rather than the KR divergence is KR divergence, it can only capture the tail effect of something like x squared. But for the Renyi divergence, it will be some kind of divergence can capture the tail behavior of the x to the power 1. Okay, and for here, we just assume that we have some kind of point carrying inequality of the target density. So this is for the smooth case. And for the convergence guarantee for the non-smooth case, actually the thing a little bit tricky. And you see that I put the informal in this theorem over here. So the reason I put the informal over here is I did not really specify the choice of H and also the constant CK over here, because the choice of H and CK over there, it will be very, very long. Otherwise, I will use 2 or 3 slides to give you the restriction on the H and the constant over here. But the thing I can promise to you is we can get some kind of convergence for the non-smooth distribution. And for the first scenario, we got some kind of convergence regarding the average distribution, which is some kind of sublinear convergence for the KR divergence. And for the second scenario, we can get some kind of linear convergence for the W2 distance. And essentially, the error for this theorem, or the low order, or the dominating order of the error, actually coming from the score function approximation. It's actually something keep being observed in many, many applications. This kind of approximation for the score function is actually the major source for the error over here. So this is actually some kind of error coming from the Laplace approximation to this kind of kernel formula, which is essentially the error comes from approximating the score function. Okay, so this is a convergence guarantee. And finally, the last thing before we move on to the numerical experiments, the last thing I want to talk about is something that I guess Dan loves a lot, this kind of total variation regularization. And indeed, we can also extend something we have mentioned in the previous 10 slides to the case of the total variation regularization. So the major difficulty for the total variation regularization is for the TV norm, we do not really have good access for the proximal term. We do not know exactly the explicit form for the proximal term. But the thing we can do for the case of TV regularization is we can introduce some kind of auxiliary variable, which we call something p, and we hope that this kind of new variable p will be some kind of reasonable approximation to the gradient of the image. So for here, you just imagine that this u is some kind of image. And the thing we are trying to do is we are trying to draw some kind of samples over here. And then in order to handle this kind of TV norm, we simply introduce a new variable p, and then we put a new penalty term over here. Okay, so basically this penalty term is trying to enforce that p will be something close to the gradient of u, which is a TV. Okay, so this is the log density we will think about for this kind of TV regularization scenarios. And for this term, you can see that it's actually some kind of it actually contains three terms. We have some kind of smooth term, we have some kind of non-smooth term, and we have the third non-smooth term with some kind of linear transformation. And this kind of structure actually, I guess, will remind many of you about this kind of very classical three-operator splitting in the optimization community. And indeed, the thing we will do in the next slide is we will apply those kind of three-operator splitting technique to this kind of sampling problem. And the thing we will do, actually, we will recall some kind of very classical three-operator splitting, the conduct-Wu prime dual splitting algorithm. And actually, we can apply any other three-operator splitting technique to construct some kind of sampling algorithm. But for here, I'm just using this kind of version by the conduct-Wu. And for this case, the only difference between our algorithm and the classical optimization algorithm is we have some kind of additional score function term, which is some kind of term that gives us some kind of diffusion. So this is something that's different between the classical optimization and this kind of sampling task. Okay, so one thing that I want to point out over here is actually you see that I have some kind of reference over here. So this is a paper by the Martin Berger from Professor Martin Berger from Germany, and he's actually a few months ahead than us. And they also have something very similar like this in this year on arXiv. And in their algorithm, they are using the Brownian motion term to generate diffusion. But the most important thing I learned from the paper by Professor Martin Berger is the convergence for this system is something very, very difficult. So I read all their paper, and the thing that I learned most importantly is the proof for this guy is very, very important. So that's the reason that I will, for this part of the discussion of total variation sampling, I will stop here. I will just give you the algorithm, and for the convergence of this kind of prime dual splitting algorithm, if you have any idea about the proof of the convergence, please feel free to talk to me during the offline time. Okay, but anyway, for this algorithm, it definitely will work. I will give you some kind of numerical experiments about how this algorithm will help us to draw some kind of samples with the total variation regularization. So finally, I will give you some kind of numerical experiments. Since I only have 2 minutes, I will go through very quickly about the experiments. So the first experiment we are doing is some kind of experiment in the 50th dimension. We have some kind of Gaussian mixture distribution, and the benchmark algorithm we are trying to compare is some kind of modification for the unadjusted one. So for this case, we actually have some kind of, so we also have some kind of proximal operator appears in this kind of variant on one in order to handle the non-smooth term. But anyway, the major thing we will learn from this experiment is you see that the blue curve is the decay or K-R divergence for our algorithm. Because our algorithm is some kind of deterministic algorithm, you see some kind of pretty smooth decay of the K-R divergence for our scheme. However, for the case of you have some kind of Brownian motion, you have some kind of pretty serious oscillation. And especially this kind of, when you go to the really high dimension, this kind of Brownian motion based algorithm will give you not so accurate estimate when even you run this kind of things for very, very long time. Okay, so this is the first toy example for the Gaussian mixture distribution. The second example is for the case that we have some kind of total variation regularization on the image, and simply we are trying to draw some kind of samples from the distribution f plus this kind of total variation regularization term. And this is the exact image, this is noisy image, and this is the mean of samples we draw after 100 iteration, and this is mean of samples that the Wunga will draw after 100 iteration. And you see that for this case, we got a much better image compared with the case of you simply using the Wunga. And one comment over here is the reason that we want to do this kind of TV denoising for the sampling is the real application for this kind of setting is it's something very useful in the medical imaging. It will help us to determine the uncertainty level of your recovery. Okay, so this is a real application for this kind of drawing samples from the total variation regularization. And finally, the last example I want to show you is some kind of Bayesian neural network training, and we are trying to compare our algorithm with, again, the variant of WUNA and also the SVJD, other very classical interacting particle system for sampling. And in that case, you can see that we also get some kind of some kind of slightly better result than the classical algorithm with a similar computational complexity. So finally, here is the conclusion. And so I guess the most important message for this work is we are trying to use some kind of regularized Wasserstein proximal operator to get some kind of semi-implicit scheme. And also we are trying to use some kind of splitting method so that we can handle some kind of high-dimensional distribution, or we can approximate this kind of kernel formula appeared in the regularized Wasserstein proximal operator. And also, finally, we also have some kind of convergence guarantee about algorithm, which is built on some kind of tools from the optimization theory. And for some kind of future direction over here, one thing that we want to do in the future direction is, for now, all our analyses are in the density level. So some kind of very important question we need to answer is what happened for the finite particle system, and what happened for the convergence for the finite particle system. So this is the first future direction, and the other direction is for most of our analysis for the time being, they all built on some kind of like the log subordinate inequality or the point carrying inequality or some kind of convex assumption. And we are trying to think about how we can extend this kind of analysis to the non-log concave distribution. And also another future direction is maybe how we can use the softmax structure that appeared in our algorithm to design some kind of new layers in the for the neural net for the machine learning. And here is a preprint for our paper. And so I guess I will stop here. Thank you very much.